Hi, my name is Barbara Fanning, and I'm with the San Diego Green Building Council, and I'm here with Ted Hyman and Mabe from ZGF Architects to talk about the Venter Institute. So I'm just going to ask you a few questions about the work that you did at the Venter Institute. And the Venter Institute, it's actually the first net zero energy laboratory in the country, in the world. Yes?
In the country, not sure about in the world.
Okay.
Best we can tell it is.
Okay.
We haven't heard otherwise.
Okay. And it's a LEED Platinum facility? Okay, great, great. Can you talk a little bit about what the Venter Institute is? What are they doing down at the Venter Institute?
You start. So they are doing research in genomics. They mapped the first human genome, Craig did, and they're doing a lot of work in genomics. They're working with the Cancer Center at UCSD and the med school. They have another project that Craig did a couple years after mapping the human genome, where they circumvented the world, stopping every 200 miles, collecting seawater, isolating organisms in the seawater, and identifying 6 million new genes that no one knew existed before. And so they're doing work with Scripps Oceanographic Institute on that work. I think it's about 2.5 years ago, they created life from scratch, building it up, building the DNA up, and implanting it and actually creating the first man-made organism. And then they're doing a tremendous amount of work in terms of sustainability, looking at alternative forms of fuel. And so this institute really puts all those researchers together, collaborating with UCSD, with Scripps, and other institutions, really in a whole broad range of areas, but most of it related to genetic research.
Yeah. And then I think one other important part of it is that they've got a whole group that's really focused on the ethics of this kind of research and the ethics of potential therapies that might come out of this kind of research. And if you're going to invent a new form of life, it raises all sorts of ethical questions. So they're very focused on that too. What are the policy effects and the social effects of the science that they're pursuing?
Mm-hmm. Wow, they're doing some great things. It's exciting.
Yeah.
So when you were approached by the Venter Institute to build the laboratory, we all know that laboratories have a lot of energy and water performance issues. They just use a lot of both of those resources. So when building and designing the lab, what were some of the strategies that you implemented that could help overcome the challenges of a typical lab when it comes to water and energy usage?
You want to take that first?
Sure. I mean, I think there's the obvious things, the mechanical systems in the building. I think the behavior, looking at behavior and how we can change the behavior of how things are done in a lab. Simply just closing fume hoods is a huge effect. We implemented a system in the building electrically for connected loads, which is the biggest single load in the building, where normally in a lab building you have emergency power and regular power. So things that have to stay on, freezers, get plugged into the emergency power. It's a red plug. In this case, because of the phantom loads you have on all this equipment, they chose to implement a third flavor of power, and it's the green power. And so in the labs, the raceway has red plugs, white plugs, and green plugs. And the green plugs essentially turn off at night for all your equipment that you really don't need to stay on all night. And that had a huge impact on energy savings. Things like that with all the equipment, the freezers we talked about. They're probably the single biggest heat loads in a lab building, and really using water to cool them instead of air had a dramatic impact on it.
We looked, because a lot of times in the design of buildings, in fact most of the time until recently, all of these kinds of design criteria were based on theoretical loads. People would sort of say, I got to have X watts a square foot or something like that in my lab, and without any real knowledge of what you're actually using and whether you really need to supply that much electricity to the building or not. For example, I mean, you could look at all kinds of systems that way. So we really spent quite a bit of time working with Venter while we were in design and measured their existing plug loads. And then they got kind of interested in this. The scientists themselves got interested, and they started saying to us, are there ways, help us, and they started asking each other, are there ways that we can green our actual scientific protocols? And they kind of got way out ahead of us. They were already starting to think about that, do that, ask those kinds of questions while we were still in design. And then as they moved into the building, they really started to apply some of these new protocols, you know, working with smaller quantities of chemicals, for example, all kinds of questions like that, which would, you know, reduce the demand for fume hoods, which would, you know, reduce the demand for electricity, you know, for air, so forth.
Okay.
Can you think of
There's
any
lots
others?
we could
There's
go on.
just all, yeah, there's
No, it
a
was a
ton of
client
those.
that was willing to look at everything. I
Yeah.
mean,
And the scientists were really excited. Craig was excited, and the scientists were excited about, hey, we can really rethink the way we're doing stuff in the lab, the way we're actually doing science in the lab, and have an effect.
yeah. If I think about the way they mapped the genome, you know, which was done, I think it took 30% less time and millions of dollars less, and it was about thinking about it in a very different way, you know, and inventing a new way to go about mapping the genome, which was remarkable.
Random sequencing.
Random sequencing. Instead of starting from A, you know, and going to Z, sequencing the genome, they did it in a very different way.
In a very random fashion.
Yeah.
And used the computers to put it all back together. Revolutionary idea. I think the idea of designing a building for them was the same. How do we take all that stuff and just look at everything at the same time in a very different way and put a building together unlike anybody has done before?
Well, speaking to that, you did talk a little bit about the process that you followed and how the building came to be. You employed somewhat of a what-if concept, which to me is very unique from an approach of working with engineers and scientists as well as just in the building space. So how did that what-if approach work for you? How did it work? What were the good things about it? What were the bad things about it? And how did it help maybe push the envelope for the innovation and the design and the technology?
Go ahead.
Well, I mean, that kind of what-if approach, maybe it's a part if there's a good description of the scientific method, maybe it's a part of that. It's actually as basic as that, rather than moving through the design process with a protocol that you've done before, you know, just asking yourself, you know, not all the time because you have to get things done, but asking yourself at key moments, and also I think cultivating a culture that asks, in other words, a design team that asks each other, what if we did this? What if we tried that? Rather than just always following your nose and saying, last time we did it that way, so, you know, we'll do it that way again. You say, what if we did it this way, or what if we did it that way?
Traditionally, I think when we start, you know, if we think back before we had done this building, traditionally we'd start design, you'd get a site, you'd get a program, you'd start to think about how it fit on the site, you'd start to come up with an idea about the architecture, and then we'd call the structural engineers in and figure out a structural system to go with the building. And then once you got that kind of worked out, you'd bring in the mechanical engineers and try to figure out how we're going to air condition this thing. And then after that, you'd bring in the landscape architects to figure out about the site and the landscaping. And then, you know, lastly, we'd probably bring the civil engineers in to figure out how to, you know, drain the thing. And in this case, we started with everybody in the room at the same time. And, you know, it was really interesting.
On day one.
Yeah, the very first meeting was everybody, and it's kind of like, why do we have all these people here? You know, we don't usually bring them in for another 3 or 4 months. What are they going to bring to the table? And I think what they brought to the table was a really different way to look at, you know, designing a building.
So that unique approach with that what if and bringing everyone into the room really lend itself to using an integrative systems and design approach where all the pieces fit together. So can you talk a little bit about why that approach was really important when designing a space like the Venter Institute, or why that's so important just overall with bringing all the pieces together for overall sustainability?
I'll turn it around a little bit, because I think it was, you know, we designed the thing, and then we actually got a budget, you know, later on, and we were over that budget, and so we had to come back and figure out things, you know, value engineer things out of the building. And I think the light went off when you realize, you know, we were talking about value engineering things out of the project, and if we took them out, it was going to cost more money someplace else, and that when you actually get the thing down to where every system in the building is relying on every other system, and it's the most efficient, cost-effective way to do it, you kind of got it right, you know, and that there were things we just couldn't value. You know, you couldn't value engineer the mechanical system, or I would have had to spend more on envelope, and I would have had, you know, all these other things. And to me, that's where, you know, the building is really integrated. It's, you know, I've gotten a building that's the most efficient way to put the different systems together and rely on each other to work.
And I'd say another way of saying what Ted's saying is that every system has its basic job to do, but it also has more to do. I mean, for most of my career, and in your career too, we would think and talk about the envelope of the building, meaning the facade, the skin of the building, as the skin. But what if we thought about the skin also has a mechanical role? It's a part of the mechanical system of the building. If you design the skin, you know, to reduce heat load on the exterior of the building, for example, in a way, and shade itself and all of that, it's actually part of the mechanical system. And you could go on and on and on. And that, to me, that's what integrated design means too. It means getting everybody around the table, but it means everybody has a hand in the envelope. Everybody has a hand in the structure. Everybody has a hand in the mechanical system. Rather than sort of saying, you do this, you do that, you do that. We'll do all that together.
So just talking a little bit about some of the systems, could I get you all to explain a couple of the systems, maybe the daylighting system and the water conservation system? Just a little bit more. We have a diagram.
You're our water guy, Ted.
Well, let's start with some of the most basic of the systems. So, I mean, I was just thinking about the envelope as you were talking. So I'm looking at the envelope. It's got operable windows in the offices, and it's got fins to block from the late afternoon west sun. And so, you know, I really couldn't take the fins off of the building, or I'd have to buy more chilled beams inside the building to cool the space, and that was great.
So the fins are part of the mechanical system.
And they're beautiful.
Yeah, the windows, you know, so now we have windows, but I've got them in a building that's essentially air conditioned, which everybody says you shouldn't be doing, you know, especially in California. And so what we did though is we wanted to come up with a way that the users of the building could really take ownership of the mechanical system there and be part of that system. So there's a light in every office right next to the light switches. There's another light that's got a green and a red on it. In the open workstation areas, there's a light up in the ceiling, and I think they can actually, once the whole system is working right, they can actually see it on their computer. That when the light is green, they're supposed to go open their windows, or they can go open their windows and get fresh air. You know, when the light's red, it means you got to turn, you know, close your windows. And the problem is if I'm not there, and then what am I going to do? And so this was so valuable because they really loved the fresh air there. This was so important to them that at the end of the day, the security guy, as part of his detail, he has to walk through and close all the windows, you know, when the red lights go on. But so the users are actually in some ways part of the control system, and the security guard, who otherwise is going to be sitting at his desk all night long, participates in the mechanic.
Gets a little exercise.
Yeah, gets a little exercise.
Walks the building. And
but it's saving
out.
A tremendous amount of energy for the building. So, you know, how do you take that every step of the way? And I think, you know, the labs, you know, there's all the, you know, the plugs, there's these types of things. It's all the simple things people can do to really affect the environment and the cost to operate the environment. And once they're educated, and you know, when that light's on, I can go open my window in my office, and if it goes off, I know I really need to close that to save energy. I think it's really amazing to watch people. They kind of all get up and go close their windows. So you wanted to talk about.
Well, I think you talked a little bit about airflow with windows, but
Yeah.
you know, thinking about the daylighting and that sort of approach to, I guess, daylighting with productivity and just not needing to turn on the lights or anything like that.
Well, there's a lighting system, a digital system in the building that's controllable, but the big idea is that in that office wing, or in the lab wing, on the south side, I've got large overhangs, so I almost never am going to get direct sunlight in the labs from the south. Even as the sun clocks around to the west, there's a fin on every one of those, so I've really protected on that side. On the north side, I'm looking into the courtyard, so there was a lot of studies. We did a lot of modeling, both physical and computational, that how am I going to get daylighting through that PV array down into the space and get it reflected back into the offices. And we had some scenarios actually early on that actually let more light in and was kind of a diffuse array, and it turned out that, you know, when you really look at it, the noise, the visual noise of that was going to be...
Shade and shadow patterns on the facade.
So we spent a bunch of time trying to get that to where it's calm, but still lets plenty of daylight in. You know, a lesson learned on the south side of the office that opens into that courtyard, we figured that PV array is still shading more than 50% of the light. We value engineered out the vertical shades on that side of the building, left the pockets. It's a problem now because the light is, you know, it's coming in, bouncing off that floor, and those people are getting glare in there, so stuff is going up on the walls and the shades are going in shortly. So even with the modeling where you thought it was right, sometimes you're a little, you know, there's always the surprise.
But you want to have the solution in your hip pocket, like we all said to each other, in case we need the shades here. There'll be a place for them. It won't be an add-on.
So, and then as I said, the north side of the offices have those vertical fins, and that's actually working really well. Nobody's papered their windows yet. And it's partly they have incredible views, but it's partly because we really are getting the light, you know, that glare issue solved on that side of the building. So the lab building, as the light comes in, and we have adequate light, the lights on the perimeter actually go off, and so they can move in. When I'm really getting good daylighting, only the middle band of lights stay on. The rest of the lights are off in that space. So, and they can override it if they choose to, but you know, it works pretty well. And same thing happens on the office side, although there's more control on the office side because you have private offices.
And I was going to say too, two kinds of modeling. Digital modeling, all of this went through digital models. It also went through physical models.
It went to the daylighting lab in San Francisco.
Yeah, at the Center for the Built Environment.
And now the big test is the people.
People. And both of those tests didn't clue us into that one problem I talked about, so it's interesting.
You can't get little tiny people to react the same way either in the digital model or the physical model, so there's always something to do when people move into the building and really learn to live in it.
Well, that's great.
We also try to, I mean, this is an aside, but we try to say to our clients, you know, we're breaking new ground here, and particularly with a situation like Venter, we're breaking new ground, and we want to give ourselves hip pockets because, you know, we're trying something new, and we want to be able to adjust it as people move into the building in case it doesn't work. And that's I think that's part of what we've really learned with our first generation of net zero buildings too, is that these buildings are complicated. You have to learn to live in them and live with them, and you're part of the systems. The occupants, the inhabitants of the building are part of the systems of the building.
Probably you know, from a mechanical standpoint, the two big energy saving approaches was one, you know, heat recovery both in water to water systems and then air to water systems as backup. And the other was the idea of the chilled beams, which, you know, hadn't been really used in the US very much. I think there was one building in Washington in construction when we were doing this building. I may not have even started, but it was this idea of taking a look at what's the minimum allowable air change rate for a lab building and setting that. And at the time, the EH&S people, Venter's EH&S people, and they relied on UCSD's EH&S people as well for discussion, was 6 air changes. So the minimum amount of air you could, if there was nobody in the building, you could put 6 air changes in there, and that would be, or if there was no chemicals in the building, and that was safe. And we said, that's all the air we want to put in the building. And so all the rest of it is done with the chilled beams, which essentially puts that air into the space with high velocity nozzles and then has a cooling coil or a coil in the space, and you can run chilled water through that, and it creates a Venturi effect and actually cools the air with the water. And then in the winter, if you actually needed heating, you could put hot water into that coil and you know, heat the air up. And then what we did from that was there's a whole series of manufacturers now. Aircuity was the first one that are doing air monitoring. And so there's sensors in, I forget how many we have in the building, in all the lab spaces. There's multiple sensors that are sampling the air, and they go through a cycle. It takes about 10 seconds per point. They go through a cycle sampling all the air in the space. And we convinced the EH&S people that we could push the occupied limit down to 4 air changes with that system, with the ability to ramp up in any one space if there's a spill. So it's inherently less energy, but the other side of it was if there's a spill, it's incredibly safe, because it's going to pull a lot more out than a conventional system would be. So we're down to 4 air changes and 2 in unoccupied mode, which is a dramatic savings in terms of just the amount of air going in the space, which, the chill beams were more expensive, but if I think about that, if I can get rid of air handlers and downsize all my ductwork, I can pay for that stuff. And that's the kind of strategies that we talked about for all these systems.
No.
I'll let you talk about the complicated heat recovery tanks.
Actually, we might make Peter talk about that.
That would be good for Peter to talk to those.
No, that's good. It's good.
Yeah.
Peter should talk to that.
And are there any of these others that you would want to talk to?
Well, this is just the monitoring systems, and and Peter can talk to this too, but virtually everything in the building goes back to a building information system monitor. So it's the fire life safety, the mechanical controls, all the energy management, so I can see what I'm really using, lighting and the lighting controls. As I said, that's all can be done via the computer. I can adjust things, and we talked a lot about, there's dimming on the thing, and I could effectively come in every day and dim the lights in everybody's offices by 1% and just keep cranking it back to a point that people start complaining, and then I know I've gotten to, I've gotten to the spot I need. So really interesting. The building dashboard, obviously, if people can see what they're using, hopefully down the road we can get them to compete with each other to behave better. The security systems in there, and all the irrigation control systems. So there's one place that you can really control the entire building.
I think I just have maybe one more question for you. So what words of wisdom or advice can you give to other organizations that are looking to build a net zero energy building or laboratory? What words of wisdom do you have?
Go ahead.
I guess I'd just start off and say, don't shy away from it. Push it. Find the edge, given your particular circumstances, given your budgetary constraints or not. If find what really works. Don't be afraid to look at how you're doing business, how you're, if you're a laboratory, obviously, how you're doing research. We talked about that, the fact that research protocols were in question too. Don't be afraid to re-examine anything you're doing in the building and the way you're living in the building. And I think probably most of all, carry a spirit that this building is going to be an extension of me, it's going to be an extension of our organization. I'm going to be living in it, controlling it, using it, and I need to understand and be part of how all that works as a total set of systems. And don't forget that the people that are inhabitants are really the inhabitants are going to make the difference over the life of the building, whether it really works as a net zero building or not.
I think the other thing I might add is just because it was a group, I think almost the entire team had never worked together before. Craig wanted to help pick all the consultants, and so we came in with a team in the interview, and he said, that's great, but I want to interview all your consultants with you and have a discussion about it. And pushed us. We hired more consultants than we'd ever hired. We had different people and different consultants than we would normally have on a lab building. And I think everybody, everybody came to it with this positive attitude and an idea that everybody around this table is going to help contribute to getting there. And it was one of those experiences, that you won't forget for your life. And I think you can always go into every building that way and think about, how am I going to bring together a group of people, maybe not the people I'm comfortable working with, to really do something special.
Actually, people that are going to ask questions, and make you a little uncomfortable.
Yeah. No, there were a lot of discussions.
We never came to blows exactly, but but there were a lot of questions and disagreements, and we can't do it that way, and then come back later. Well, maybe we could do it that way.
Yeah. Conflict was kind of a good thing.
Actually, it was. Conflict in the sense, not open warfare, but conflict in the sense of not being afraid. It was a cultural situation working on Venner together with that team where, no one was afraid to put an idea out there. No one was afraid to ask a question. It just was no fear. Let's do this that way, don't you think?
Yeah.
And then I think the other part of it was the client was always there right with us. We would have these big workshops, And we not only had this big consultant team, a lot of people and kinds of people that we hadn't necessarily worked with on all the projects we work on. And coming out of that method of collaboration with the client and with that big team that Ted described, that's the way we almost insist now that we work on every single project. We don't like to work any other way.
And I think in the end they got a building that they didn't have to give up anything. I mean, I think if you ask them, they didn't give up anything to get, you know, a net zero building. They got a lot of things. They got a really great environment to work in. It's comfortable. It's, you know, it's really conducive to the kinds of work they're doing, and just, I mean, people are just hanging out. It's a great place to be, and so that it improved their quality of life rather than, you know, sacrificing something to get that. And I think that's really important, that you can do these kinds of buildings and get, you know, the quality of life can be raised rather than having to sacrifice it to have it.
That's great. Thank you so much for sharing with us today. I think it's such an amazing space, and we're just honored to have got to meet you and talk about it and learn more about it.
Thank you for having us.
Too.
Thank you very much.